Okay. Hello and welcome to the Video Research Workshop. I'm Andrea Langrish, Managing Director of the Center for C-SPAN Scholarship and Engagement. This workshop is hosted by the Center for C-SPAN Scholarship and Engagement with the advanced methods at Purdue in behavioral health and social sciences. To tell us more about the workshop is Dr. Robert Browning, Professor and Faculty Director of the Center for C-SPAN Scholarship and Engagement and the Executive Director of the C-SPAN Archives.
Welcome, everyone. This is an exciting time. We've had these workshops for about 2 to 3 semesters, but this semester we decided we were going to focus on video. A lot of the workshops have focused on textual analysis using closed caption or mostly closed caption from the videos. But this semester we decided, well, let's give people some understanding of what you can do with video. And so we have 3 workshops. Today, Ed's is sort of a primer, sort of give you an overview of how video is organized. And he's also developed a couple tools he's going to let you have access to that will let you extract frames or look at the audio record of the video. And so we're excited about that. I've known Ed for many years. We've worked together on lots of projects for the archives, and he's one of the premier Purdue faculty and worldwide faculty on image processing. So Andrea, why don't I turn it back to you?
Thank you, Robert. So we're excited to have leading this workshop, renowned media technology researcher, Dr. Edward J. Delp. Dr. Delp is the Charles William Harrison Distinguished Professor of Electrical and Computer Engineering and Professor of Biomedical Engineering and Professor of Psychological Sciences, and a courtesy appointment at Purdue University. He holds a PhD degree in electrical engineering from Purdue University. His research interests include image and video processing, image analysis, computer vision, image and video compression, multimedia security, medical imaging, multimedia systems, communication, and information theory. Dr. Delp has published and presented more than 500 papers. Dr. Delp is a fellow of the IEE, a fellow of the SPIE, a fellow of the Society for Imaging Science and Technology, and a fellow of the American Institute of Medical and Biological Engineering. Welcome, Dr. Delp.
Okay, let me go. So I'm Edward Delp. Hello, and it's good. I thank you for the introduction. That was much more than I deserve. But anyway, thank you very much. And like I said, Robert mentioned, we have known each other for a long time. Back in the days, I remember Robert coming to my office, that little cupboard that I had as an office in the EE building, and he was talking about the C-SPAN archive starting up. And that's when Robert was still doing things on videotape. Remember that, Robert? I'm sure you remember.
Oh, yeah.
And all the videotapes. So I think probably those are probably still around somewhere, but everything's gone digital. So I'm going to give a very brief talk today. And all of the slides and everything is available. And so we'll talk about this, and I'm going to, we'll have some little tools you can play around with at the end. So if you want to learn more about what I do and what my lab does, you can, hopefully you can see my cursor, you can go to this website, which is my website, and that will take you to the Viper Lab website. This is the video and image processing lab website. So if you want to know more, particularly about image analysis, I have created some very basic lectures that are introduction to image processing. They last about 2.5 or 3 hours. This is much, much more than I'm presenting here. You can get a copy of the slides and the videos, and you also will tell you we can get a copy of the slide decks. You can get access to all these links, but you can get a copy of these of this tutorial presentation that I put together, and you can watch this if you like, or just look at the slide deck. So you're more than welcome to use it and take a look at it. So let's talk a little bit about digital images. Okay, so what is a digital image? So let's talk a little bit about this. So if you think about it, you have a camera. That camera, let's say it's a camera on your cell phone, there's a lens, you sort of point it at something, the light reflecting from that object or maybe some direct light from maybe some sort of source, like maybe there's some lighting in the room, enters the lens on the camera focuses it on some sort of sensor. And then what happens is that light has to be converted into a digital image, okay? In the old days when, and this is, you people are all young, so probably none of you remember having a film camera. The sensor was a piece of plastic with some chemicals on it, essentially. And when the light hit the chemicals, some chemical reactions happened, and then you had to go through some process of developing the film and all the rest of that stuff. But as far as the digital image, you have a sensor, and that sensor essentially converts that light from the light into an electrical signal. So you can think of it before any processing or analysis of an image or a video, and we'll say more about video. A video is nothing more than a series of still images. Before any of this analysis can be performed on an image, a digital representation of it must be obtained. So a digital image is nothing more than a matrix of numbers. You know, it's got a bunch of numbers in the rows, and got numbers down the columns. Each entry in the matrix is sometimes called a picture element or pixel. Sometimes very old language, they also called it a PEL for actual pixel element, but most people call it a pixel. The value of each pixel corresponds to the amount of energy in the image at that particular location on the image. Now, one of the things that, you know, most of the work you guys are going to be doing will probably be images that will form, like if you're using a C-SPAN imagery, this is imagery that's formed with visible light. But images, and what we do in my research laboratory here at Purdue, we look at images that can be formed from ultrasound, radar, gamma rays, electrons, infrared signals, X-rays, and something called nuclear magnetic resonance. So you can form images from any type of light. But what you have to do is you have to convert the image into some sort of electrical signal. So one way of thinking about this at a very, very high level, you know, if you actually look back at, you know, stand away from the screen, this is the picture of Abraham Lincoln, but it's very highly pixelated because I wanted to show you with each one of these little boxes here, this is a pixel, okay? So you can think of what you do is you start with a transducer or a sensor that converts one of the forms of energy, like a electrical or light, into electrical signal. Now, in your cell phone camera, that is a particular type of sensor called a CMOS sensor that essentially light shines on it and converts the light to an electrical signal. So you can think of the transducer moving from one pixel box to the other. And again, it doesn't quite do it this way, but in a stylized way, you can think of that. And it asks the question, it measures the amount of light at each one of these locations. These are sometimes called spatial locations. And the amount of energy that you see, like over here, you see that this energy that it measured was 157. That would correspond to how much energy that the sensor is seeing at that particular location. And it corresponds to the grayscale, the gray level of the image. Now, if you're doing this in color, you would have a color sensor that would measure the color both in the red, blue, and green, all three of the spectrums. So this can be thought of overlaying sort of a grid on top of the object. And so again, what I did here is, you know, here's this highly sampled version of Abraham Lincoln. Here's what each one of the sensor measured at each one of these locations. And then this over here is what is the digital image. So a digital image is nothing more than a matrix of numbers, okay? So again, here's another way of thinking of it. You know, here's some object. This is a much more simplistic picture. Here's an object. You have some sort of grid, sometimes called a sampling grid, and then this is the amount of energy. So each of these grid boxes, or each one of the entries in the matrix, is known as a pixel or pixel element. And then the grid is usually described by the number of pixels on each side, like maybe it's 512 by 512 or 1024 by 1024, or much larger than that, particularly if you're looking at cell phone cameras. The process of this sort of overlapping of this grid box and then measuring the energy, this is sometimes called spatialing, sampling or spatial sampling. So again, what I want to leave you with is that digital image is nothing but a matrix of numbers. So anything you can do to numbers on a computer, you can do to a digital image, okay? Now, some people think the advantage of a digital image is that it does not degrade with age. Now, could be a whole separate lecture. One of the problems with a digital image, like any type of computer file, you're going to keep it on your computer in a file system. That file system, if that hard drive fails, and hard drives do fail, the image is going to maybe degrade, or maybe you'll lose the whole thing. So just like analog technology of images, photographs, or printouts or something like that can degrade with age, that also is true for digital images, and it's usually the storage medium that degrades with age. But again, the emphasis is that a digital image is nothing but a matrix of numbers. Okay. All right. So here's the problem with a digital image. It takes up a lot of data. A typical 1024 by 1024 image, this is like a 1 megapixel image, and your camera has 10, 15, 20 megapixel cameras now. It has 1,048,576 pixels. If you look at how much data this corresponds to, and again, I wish I had more time to describe this in much more detail. If a 24-bit per pixel image, this is going to be 25 megabits of data. 1,000-word text file typically is about 56,000 bits. So you can say a picture is worth more than 10,000 words, maybe, if you want to look at it this way. So again, I wish I had more time to talk about this particular thing, because a lot of people sometimes don't understand this phenomena. So is having more pixels better? In other words, is a 20 megapixel camera inherently take better images than a 12 megapixel camera? And the answer is no. Okay, more megapixels doesn't give you better images. It really has to do with the entire system, the hardware system, of how that camera takes the image. And it has to do with the sensor size. And again, if you look at the little tutorial course I mentioned on slide 2 or 3, I actually give a 10-minute discussion about what I mean by the sensor size. And so one takeaway here is, more megapixels doesn't necessarily mean a better quality image. All right, what happens then is, if you go back and you have this matrix of numbers, you want to be able to store it on your computer. And there are various ways of doing this. There are many file formats. Typical one that maybe you may run across is something called JPEG or JPG. This is actually a compressed format. Other images you may run into are PNGs or GIFs. If you're doing any type of scientific imagery, you might run across an image that's sometimes referred to as a TIFF. One of the things that's important is that, again, I wish I had more time to talk about it. When I see my camera is on. So, when you take a picture with your cell phone here, and you take the JPEG file out, or if it's an Apple phone, it might be with the Apple extended image format. One of the things you should know is there is metadata for that image that is stored inside the image file. And this metadata can even include the location. So when you exchange images with people, if you don't particularly want them to know the location where you took your pictures, you might want to consider, doing something to the header of the file, remove this stuff called EXIF. If you Google EXIF, there's lots and lots of things you can read about that. But it's a standard that all digital cameras use. Video cameras use something somewhat similar to it. It's not exactly EXIF, and there's all kinds of information that's stored in the EXIF file. One way you can see this information, let's say if you're on a Windows system and you highlight, let's say a JPEG file, just click on it and then do a right click, and then scroll all the way down where it says more info or about or something like that. You'll see all the information that's stored, including you might even have the location of the particular file. Okay. So again, I want to emphasize that all image processing does is it takes these pixels and plays around with them and extracts information. I'll say a little bit more about that as we sort of go forward. Okay, so my slides are stuck here a little bit. So let's talk about video. And by the way, if you have any questions in the middle of my talk, please stop, turn on your mic and ask the question. We'll have lots of time at the end to answer more questions. So what is a video? So this is an experiment. This is, I can't pronounce the guy, Edward, I guess, Mulbridge. This is his horse experiment. So this was essentially, this settled what is known as a bar bet, bet or a pub bet. This was a bet. The bet went like this: is a horse is running. Is there any time when the horse is running when all four legs of the horse are off the ground? Now, just watching the horse run, you may not be able to see that. So what they did is they took a bunch of still cameras and they aligned them, they put them along a place like a racetrack. And then as the horse ran through, there was a tripwire and the horse literally tripped each one of the cameras as it ran by, and you captured this series of images. And you see immediately the bet was solved, because if you look at this image right here, I think everybody can see my cursor, in this image right here, in this image right here, and probably some other ones, the horse's legs are completely off the ground, okay? So this was an example of trying to capture motion information. Now what happens is you have all these still images. Now, if you display these images with some sort of a display system in a very rapid manner, this is what you see. So again, you can think of a video as a series of still image that are acquired in a time sequential manner, so that when they are played back and displayed on an appropriate display system, you perceive motion. Okay. Now, in the United States, how does it for video? A video frame, one image is taken every 30 seconds. So you have 30 frames per second. That what I told you is not exactly correct. It's actually, depending upon the video format, it could also be 29.95 or 94 frames per second, but just think of it as 30 frames per second. And by the way, you see the same thing when you go to a motion picture where they actually use film. Now, most motion pictures are digital, but in the old days, you went to a motion picture and they actually played a film, and that was recorded at 24 frames per second. And then it was just displayed very rapidly. And then you as a human, your eye then perceives motion. So again, so for a typical video, you'd like to know two things. You'd like to know how big each image is, like how many pixels by how many pixels, and what is the effective frame rate. And I'm not saying a lot about color and color spaces right now. Again, if you take a look at my little tutorial that I mentioned earlier on, I do talk about colors and RGB spaces and a few other things like that. Okay, so again, this idea is you have a series of still images that are called frames, where you can think of, this is frame 1, this is frame 2, this is frame 3, this is frame 4. And then you have some sort of device that allows you to capture these images in some sort of a time sequential manner. And then you have another device that allows you to play them back, then you will perceive motion, okay? So here's a little commercial about Purdue. So Purdue University has been working in the area of video and TV since the 1930s, okay? So these three gentlemen here were all electrical engineering professors in the 1930s. And this TV that you see right here was one of the first all electronic TVs that was ever made in the United States. So this shorter gentleman here, his name is Roscoe George, and this is George Heim. And this television, it used to be, but I don't think they have it back in yet. It used to be displayed in the MSEE building. And I think they're going to be redisplaying it again. The Smithsonian Institute would love to have it. So we've been doing video and digital image processing and video processing for more than 75 years here at Purdue. There's actually some other, I can point you to some other information about the history of TV at Purdue. Here's a brief history of TV or video. What is the difference between television and video? Generally, people think of television as something that's transmitted over a cable system or through the air. Video maybe is a digital signal that maybe is streamed, or you have something on your computer you play back. There was, 1900 was the first time television was used. There were earlier TVs that were not electronic at all, but were mechanical. And actually, Purdue does have 2 mechanical TVs. You know, Purdue ought to have a museum, but there is actually 2 mechanical TVs that are not displayed, but are located in storage in the basement of the electrical engineering building. What happened then in the 1930s and 40s, TV was experimental TV was going on. As a matter of fact, at one time, there was a period of about 3 or 4 months in the U.S. that the only television station I think it was 1938, that was broadcasting east of the Mississippi River was the one located in West Lafayette, Indiana, at Purdue. The TV studio used to be in the electrical engineering building. Okay, so then World War II sort of halted all this. And after World War II, television exploded in the US and the rest of Europe. And so you have color television coming on about 1954. And then you had digital in the digital transition in the 1990s. Okay, so again, I want to emphasize, again, anything you can do to a matrix of numbers, you can do to an image. So here's some of the things you might hear about, different types of video. I'm going to concentrate on these last 2. This last one is high definition television. The spatial frame sizes are 1920 by 1080. There are some other formats here. So when you hear people talk about for a 4K TV, like right across from the room I'm sitting at, there was actually 2 4K TVs. So that means that I can't remember what the first number is, but the last number is 4096, and then this is proportional to that. So you can see these are very, very large, getting to be very, very large images. A standard definition television is sometimes 720 by 480. Okay. And let me tell you one of the problems about digital video. So I'm not going to explain what all this nomenclature means, but let me just, if you had an HD TV signal, which is 1024 by 1024, and you were transmitting this in what is known as a high res mode, which is 60 frames per second and not 30 frames per second. And this 422 has to do with something about the color spaces. You would need to be able to, you would be transmitting almost 2.5 gigabits per second to transmit that, or even to play this video out. So that is way too much data for video, because what happens is video starts taking up lots and lots of space. So what happens is people looked at this whole area of something called compression. This is based on some work in information theory that was first described by a man by the name of Claude Shannon in 1948. And what he basically said was data, particularly sensory data like audio, images, and video, all have inherently redundant information that you as a human looking at it do not see that or notice it. So you can think of this as the goal of this compression stuff is to remove redundancy and to come up with an efficient binary representation of information. Okay. And there's been a lot of research in here. My PhD dissertation a long time ago was based on one form of this, of image compression. And so what happened then is in the late 1970s, people were, digital imaging was really going to get to be big. Okay. So some international standards groups formed to be able to standardize certain types of compression technologies. One was something called JPEG. And if you don't know what JPEG stands for, Joint Photographic Experts Group. It is a standards organization at ISO, this is the International Standards Organization. They have produced 2 standards. One is called JPEG. The other one is called this is actually should be JPEG 2000. There's a typo here, not JPEG 200. You probably haven't done much with JPEG 2000, but if you go to a movie and it's a digital cinema, they say that at the beginning, then you're looking at JPEG 2000 images. Okay. This was mainly for still images, and I can say more about digital cinema later if you want. There was another part of that standard organization, the ISO standards organization, that was called MPEG. This stands for Motion Picture Experts Group, okay? And they designed several standards, MPEG 2, MPEG 1, MPEG 2, and MPEG 3. You probably, most of you are not going to know much about or heard much about MPEG 2 or 3. This is videos that usually have these .mp4 in their file name. It turns out there was another standards organization called the International Telecommunications Union. And this was, or ITU, you can think of the ISO as being more like computer guys, computer people, and the ITU was more like the old telephone guys, okay? And this is a UN-based organization. It's located in Geneva. And actually ISO is in Geneva. And they came up with a series of video standards that have these names H.261, H.262, H.263, and H.264, H.265, and there's an H.266 out too, okay? And maybe you've heard people refer to these and you say, well, maybe what's the difference between these two? So let me just show you this. This is a little bit older, but I think it's pretty good. On the bottom is the ITU standards, and on the top is the ISO standards. One of the things that that happens every once in a while, and more so lately, is ITU and MPEG work together and they produce a joint standard. So in 1995, they produced MPEG 2, and also, which was also known as H.262. MPEG 2 is used a lot in, it can be used in a lot of things like DVDs and things along that line. They also got together and produced another standard, which has a big mouthful of names. It's called Advanced Video Coding, and it's really technically called MPEG 4 Part 10. So that's a big mouthful. So people sometimes just call it MPEG 4, or they call it H.264. For H.260, H.265, I forgot what MPEG is calling it. It might be, this is the ABC, the Advanced Video Coding Standard. So again, you may hear people talk about these. One of the things we're going to, when we talk to you about our video tools, we're mainly going to talk about using MPEG 4 files, which are either H.264, they could be H.265 or MPEG 4 Part 10. So you're going to see these types of things. And again, you know, this is, you may see files that are usually .jpg, those are JPEG files. One of the things that came out of the MPEG and ITU standards is there also is a audio or music standard. Some MP3 is one example. There's another one called AAC. So the MPEG people did both audio and video compression, and so did the ITU people. Okay. So again, for an MPEG, a typical MPEG file, what I want to show you is this picture. Usually the MP4 file is what is known as a compressed bit stream. So what goes into this file is the video, which is then compressed, let's say using H.264, the audio, which is separately compressed, and that is maybe uses MP3 or AAC. And there's other information, other metadata, and it goes into some sort of something called a multiplexing system. And what comes out is just one file, not 3 files, okay? So for instance, in your research, you may want to take this compressed bitstream file, and you might want to pull out individual frames. You might want to pull out the audio. So you need some tools to be able to do that, because that's all sort of multiplexed in here together. Multiplexing, you can think, is a method that does all this intertwining. So then when you double click on your MP4 file and your video player comes up, you can see the video and you can, you know, you can listen to the audio. So this is what essentially all of these things on the left, or what is in a typical MP4 file. Now it's possible you could have an MP4 file that doesn't have any video, or excuse me, doesn't have any audio, it just has some video, and it's even possible you could have an MP4 file that just has audio. And these things can be relatively complicated. And so we're going to give you some tools that allow you to take the MP4 file apart, get a video file, be able to extract individual frames from that, and then also get the audio file and do some simple processing. And all these, the red box, these are much more complicated. It has to do with how all of the audio and video and other information is intertwined in using this process called multiplexing. Okay. So I'll just mention a couple other things that maybe you've heard of. Again, if you're doing a lot of things, particularly with C-SPAN and the C-SPAN data, you know, C-SPAN is C-SPAN is transmitted terrestrially, and C-SPAN is also on the cable system. Maybe is that right, Robert? Is C-SPAN actually transmitted over the air terrestrially? I don't know. Rob.
No,
Not-
only
okay.
only on cable.
Only on cable.
Oh, yeah.
But you know, if you want to watch HDTV in the US, you can put an antenna on your house. And let's say if you're here in West Lafayette, you can get at least 3 or 4 stations. And those are all free. You don't have to have cable. That was all set up by something called the Advanced Television Standards Committee, or ATSC, in the early 1990s. And it also implicated certain things about cable transmission. I'm not going to go into this in a lot of detail. If you want to know more about this, I can tell you more about it. But in the US, we had a digital switchover from the analog system to the digital system on June 12, 2009, and it went relatively well. And so we, you know, everything now in the US and everything you're run into is digital. I'm going to skip this one. And then what we're going to do, I think, is we're going to talk about a little video toolkit that we built for you. So this is, for those of you that know something about programming, this is a simple toolkit based on Python, and it has a user interface based on something called a graphical user interface. Very simple, excuse me, based on something called WXPython. It runs on Windows 10. What it will do is it takes an MP4 video file as an input, and it will allow you to grab frames. In other words, it will allow you to maybe put a range or pick one frame, and it will extract that frame from the video. So if you want to use that one frame in your research to do something, it will do that. It also extracts the audio as an MP3 file. So you have a separate audio file. And one of the things that Professor Browning said might be interesting is we have a little tool that will look at the audio file in little chunks of, you know, maybe 1 second, 2 seconds, 3 seconds. And it computes the energy in each one of those audio chunks, and it will plot it for you. So let's say if somebody is speaking very loudly, or somebody's talking or yelling or screaming, or there's a lot of background noise, you'll be able to see this from the plot. And we're going to demo this to you right now. All right, my PhD student, Myrtle Gupta, is going to demo it. So Myrtle, why don't you go ahead and share your screen and demo, and I'll speak also when we're doing the demoing. So what we have here, just hold for a second. So I'm going to show you a link later on. You'll be able to, this is a zip file you can download, you unzip it, you look at the README file. We'll say more about this. It will tell you how to install it. You have to install, if you don't have Python installed on your Windows 10 system, you have to install Python. We'll show you how to do that. Then what you do, go close all this, Myrtle, and just highlight the file. So you just click on this file, go ahead and double click it. That little black window pops up. It just tells you Python's running, and then the graphical user interface. And we can make that a little bit bigger, okay? And then Myrtle, why don't you, actually Myrtle, why don't you drop out of this and play the 2 videos that we're going to give them. We're going to give you 2 C-SPAN videos also as part of that zip file, just as samples so you can play around with it. Why don't you go ahead and play the first one? So it's going to take a second for it to load.
Million shots in arms.
So this is
Today, nearly.
This is a CDC brief. How long is this file video, Myrtle? How many minutes is it?
1 minute.
It's how many?
1.
It's 1 minute. So this is from the CDC briefing. Why don't you close that and play the other one?
Again, including Intel's
So
announcement
this
to our
is from
investors.
the White House news conference, and you have the press secretary, Jen Psaki, speaking, okay? All right, Myrtle, why don't we go back to the tool? So go ahead and start it. And so up there, you can open a file. And he's going to open, let's say, just do the Psaki one first. Yeah, go ahead. And now it loads, and then there's a slider. Go ahead and show him the slider. You can slide that along, and you can set the start and set the end, okay? And you set the end and then you say extract, and it's going to extract all of the frames in that video and put them in anywhere you want. So it'll put them in that particular folder. And Myrtle, when it's done, go ahead and show that folder if you can.
This one?
Yep. And there you see all the frames. Okay. Now remember, this is videos 30 frames per second. So, you know, if you have a 20-minute video and you want to extract all the frames from the 20-minute video, you're going to get a lot of images. So click on one of those, Myrtle, so we can see it. And so that's what you're going to get extracted out. You can then take this image and do any other type of processing that maybe you want to do on it. Let's go back to the tool again, Myrtle. So if you set the start and end at the exact same position, it only will extract one frame. And I would warn you about the extract all, okay? The problem with that is if you have a very long video, you're going to get a lot of images and it's going to take some time to do it. Okay, there's another button on the left called extract audio. So we'll go ahead and save that audio. And let's go to your files then, Myrtle. And there's the audio. Go ahead and double click on it. And he's going to bring up some Windows player.
Again, including Intel's announcement to dollar investment in Ohio
Just
and a
keep going.
total of over $80 billion invested since he took office.
Okay.
This is the power.
So there now you have the video and audio separated. Now let's go back to the tool. One of the things we did for you is where's it at? Oh, okay. You can do audio energy analysis. So you can set how big a window size. Let's just set it at 2 seconds. And you can do analyze. And it will plot every second it's averaging the energy in the audio. And you can see like where she is probably speaking and where there are pauses. Okay, let's just make it 10 seconds, Myrtle. And yeah, it gets a little weird. Go back to 2 seconds. Now we can save this. We can save this plot that you have here, and it's going to come out as a PNG file. So go ahead and save it. You put it wherever you want. Now, why don't you display it now? Yeah, there it is, and there's the plot. So if you want that plot to be able to put in a report or something like that, let's go back to the tool. And so stay here for a second. Robert, one of the things that maybe we can do for you guys in the future is we could just take all the values of this, you know, the X and Y's, and put it like in a spreadsheet or something like that if somebody wanted to do something else to it. We didn't do that. It just came to mind. Okay. The slides for this talk and the video tools are available at this particular link. Okay, you can, the slides are a PDF file and the actual tool is a zip file. So you need to download the zip file. It's sort of big. It's about 180 megabytes. You download the zip file, unzip it, and then look at the README file, which is a text file, and that will help you install it. Okay. Here's some other resources if you're interested. Maybe if you want to process those single frames and maybe you can't afford to buy a Photoshop license, I'd advise you to look at this tool. It's a publicly available tool called GIMP. It's it's become very sophisticated. It runs on Windows, it runs on Macs, it runs on Linux. It's a very nice tool for able to do many Photoshop operations. Okay. There's another thing called VLC. This is a player. If you, instead of using the default player maybe you have on your Mac or your PC, I would advise you to download VLC because it's another type of video player, but it has a lot of interesting tools. There's another whole set of things called FFmpeg, which is another set of video tools you might want to look at. If you're interested in doing any programming and you want to write things in Python, or if you're really a very good programmer, you write things in C or C++, there's something called OpenCV, which is a library of tools. As a matter of fact, if I'm not mistaken, Myrtle, we used OpenCV for some of the video stuff. Is that correct? I didn't hear what you said.
Yep. Yes.
Yes. Another set of tools that you might want to look at for processing images is these image magic. You can go to this little tutorial at Cornell University, you know more about image file formats. If you want to learn about EXIF, here's a link for that. And then the last two, if you're interested in doing Python programming, these are some Python libraries that do image processing. And then this is the link here for the actual graphical user interface. So I think I'm going to stop there. Again, the tool we give you has all the source code. So if you really are ambitious and you want to do some Python, or you want to look and see how we programmed it, you can look at the code. It's in Python. You know, we're more than happy to answer any questions about that. And then if you can add other features, it doesn't take that much to add other features, but it might be daunting for you. I know if you haven't had any programming experience. So that's all I have. I guess I timed it pretty reasonably, I guess. Does anybody have any questions? And I'd be more than happy to answer any questions about images or video or anything about the tool, and you're welcome to use it. Professor Browning has the link and Andre has a link. And those tools are up there now. You can, as a matter of fact, I'll show you one other thing. If you actually go to that website, it looks like this. It's a very simple website. So if you if you click on this, you can download the PDF file. And if you click on the zip file, you can download the zip file, save it, and then you can save it somewhere in your computer and unzip it. So the videos tool is about 182 megabytes, but that also includes the 2 sample video files, and all the source code and everything is there. So, okay. Again, anybody have any questions?
Let me just say that the other 2 workshops, this next workshop is going to be Bryce Dietrich at University of Iowa, and he's used pixels and comparison of pixels to look at the members gathering on the House floor as an indicator of whether Democrats and Republicans are mixing together. So what Ed has shown you is sort of the basics that you can understand more of. Now his will be an application of how he did that as well as the results. And the third one will be a fellow who's done audio work, Chris Lucas at the University of Washington, WashU at St. Louis, who's done audio work of Supreme Court justices asking questions. So they have substantive interests, but they're using these same kind of tools to analyze variations. And Bryce has also done variations in sound levels on the floor, things of that sort. You could think of just the House of Commons and the shouting versus the United States Congress, and think of what you might do with audio levels, etc. So Ed's given us a basic foundation to understand how these people have done their work.
Looks like Mr. Greg Murray has a question. So Greg, go
I
ahead.
do. Thank you very much for a nice presentation, Dr. Delp. I am new to this, so I was just kind of interested in what you all are doing. And Professor Brown just gave us some examples, but I'm wondering, for those of you who are more familiar with this stuff than me, what are some ideas on something we could use your program for that you showed us today?
Well, I think, for example, Robert came with this idea of you could look at, maybe you could look when maybe there's at a news conference, maybe the president is long pauses because he's thinking and doesn't know how to do the answer or something like that. So you could look at those periods on the audio. And the video, I think what Robert is describing is change detection. Maybe when something has changed in the scene, and we could build a change detection tool. You could use that to maybe indicate, let's say if you're a C-SPAN video of Congress, maybe there's a lot more people standing on one side than on the other side, or something like that. I'm not a political scientist, so I'm making some of this up too, of course. And Professor Browning could jump in, but the idea of being able to extract some that type of information. What has changed in the scene? Maybe there's more people have walked in. Is there, is somebody now yelling, or even you could on here, if you look at it, and I played around with this a little bit over the weekend. You can even see by looking at the audio, those little average audio tracks, when the speaker changes. In other words, this is when Jen's talking and this is when somebody else is talking. And you can even correlate that with the pauses. Okay. So those are the types of things that I think you could do with this. Just being able to get out a single frame, then you might want to look at the image and see, like what's in the background or something along that line. Again, Robert, please jump in, because you have better idea of what a political scientist would want.
Yeah, I think people have looked and are starting to look at volume levels on the floor, whether that's a measure of excitability or anger or something of that sort that you can't get through the words necessarily. That's what one of Bryce's pieces that he'll talk about in the second presentation looks at. And that same way with Chris Lucas and sort of what the Supreme Court justices, how the tones of their interactions.
Yeah, I mean, you can do sophisticated analysis to get sentiment out, but that's a little bit further down the road, and our tools
Yeah.
won't exactly do that.
Right.
But people are working in that area. In my research here at Purdue, we do a lot of work trying to extract useful information from video, and even
Right.
things like how people are interacting. We've actually done a project where you could see if somebody was about to break into a fight or something like that. That doesn't happen too much in U.S. politics, but it happens, I know, overseas. Although maybe that's coming to U.S. politics, I don't know. But yeah, so I think those are very interesting things you might be able to do. But I'd wanted to start you off with a very simple tool set. If you really want to do these types of things, you might want to consider looking at how you might be able to expand tools like this. And programming in Python is not that difficult. So there are very, very good online courses to help you do some of this.
Says
Yeah.
the computer science or the electrical engineer.
Well, I understand. I understand.
No, they're teaching Python and R in political science nowadays.
Yeah,
and
they are.
Python has tools.
I mean, there are great online courses for doing Python, and there's actually a book out that it says teach yourself Python in one day.
Right.
So
Yeah. All right. Well, thank you very much. That gives me
Sure.
a better idea.
Sure.
Yeah,
sure.
Ed, let me ask you a question about scene detection.
Yeah.
I mean, it's obvious from what you did here in the small tool, and you showed C-SPAN at its best. John Stewart said C-SPAN pioneered the techniques of 7-Eleven cameras, and so there's not much change in Saki's appearance. So if you wanted scene detection, do you have to capture all the images possible and then look for changes, or you do it as you go along?
You could do it as you go along. I mean, just don't worry about talking about. Well, somebody actually put in the chat something about motion detection. I don't know if you saw that or not, but yeah, I mean, you can detect motion by just looking at frame differences. So if something you could take one frame and another frame and subtract them. If they're nearly zero, probably nothing has moved.
Okay.
If something happened and you subtract them, you could look at the difference and see what areas moved. That's a simple form of doing sort of scene detection. And
Yes.
again, like I said, somebody put in the chat about it.
Yeah, that's actually the paper from Bryce Dietrich, who's doing our second panel. That's his paper.
All right.
On motion detect and the pixelization changes. And he took the votes that were controversial and non-controversial and looked at how the sides merged together, or did they merge together? So the Democrats from the Democratic side crossed over to the Republican side. So thank you, Kayla, for posting that.
Yeah. And again, this goes down to you know, you look at the video frame as just a matrix of numbers. So if you ask the question, how much this frame changed from this frame? Well, a simple way to do it, just subtract the two. If the result of the subtraction is ones or nearly all ones, then nothing much has changed. But if in some area there's a big change in the difference, that usually indicates something moved. Okay, so that would be one way of doing it. Now we didn't supply tools, but you could add a tool like that to this video tool we have, and there's other tools out there. You know, if you and I'm you know, you have to decide what you want to do for your research, but if you do learn something like Python, there's lots and lots of this series of packages. One of them is called OpenCV, and there's lots and lots of tools for doing these types of things. So you don't have to write them, you just have to make sure you set them up so you can use them. And I also listed several other image and video processing toolbar or libraries that you could use with Python. And so that might be something, you know, people want to look at. I thought there is Python courses on campus, so that, you know, people can go down that route if they're interested. So anyway.
Very good, very good. And you can see so easily where Ed's research goes into helping people understand the manipulation of images that are for nefarious reasons.
Yeah, so I do a lot of work also looking at things like deep fakes and all the rest of that kind of stuff. If anybody's interested in that, I actually have a little tutorial on image and video and audio forensics, and I can send a link to you on that. We do a lot of work looking at, among other things, deep fakes, cheap fakes, misinformation, all the rest of that stuff. We have some tools that will take a news article and look at the image and look at the caption and the for the image and see if they match, those types of things. So yeah.
Okay. Greg, did you have another question, or is your hand still up?
No, I had another question. Thank you. And I don't.
Okay, go ahead.
To dominate the questions. I'm actually the editor of a journal, and we have a type of article that we call a research tool report. And it's a type of article where people sort of briefly introduce new techniques, new research techniques. We've done a little bit on psychophysiology. We've done some stuff on a couple of other things. And I'm wondering, what would be, in terms of possibly having one of these prepared, from say a very novice beginner level to actually being able to do something of reasonable quality, how long would it take somebody to get to that point? Are we talking days of study, weeks of study, months of study?
Well, I mean, I think, you know, I didn't look at that paper that one of your other future speakers, that the guy was doing the change detection, Robert, did he release his code in that paper so other people could use it? I didn't get a chance to look.
I don't know. I don't know. That's a good question.
So, you know, you might be able to get somebody else's code and run it. Now, the problem you're going to run into is that, you know, not everybody's code does everything you want to do. So that's going to require that you do some, maybe pick up some programming schools, and again, the skills. And I think that Python, it can be done. I think, you know, one of the things that I think I would encourage is that I think you know, your school should probably have a Python programming class in the introduction, in the undergraduate program, so students can understand some of this. I mean, look at, we're seeing students now that are learning Python in grade school, okay, and in high school. So I think, you know, the ability to maybe write some of these, there's a lot of libraries out there that you can string together things that will do sort of what you want, okay, but it requires just, you know, you have to write sort of the wrapper around it. And by the way, you can totally do this on Windows 10. I know, Myrtle, you do a lot of development on Windows 10, right? You there, Myrtle?
Yes, Professor.
Yeah, is that correct, what I said?
Yep.
Yeah, so you don't have to learn Linux or any of these weird, you know, operating systems. So yeah, I mean, I think I would say it would probably take somebody a couple months to get up to speed.
Okay.
Okay, but they have to be sort of dedicated. You're probably not going to find the tool that does exactly what you want it to do unless you're reproducing somebody else's, results or something like that. And then there's value in doing that too, of course. But if
Right.
you got a neat idea, another way to do it would be team with somebody like me or somebody else in, ECE or computer science or something like that. And that, that can help. But I think getting some experience, manipulating the data yourself is always important.
Got it. Thank you very
Right.
much.
Sure.
Mhm.
Any other questions? I guess we're sort of at the bottom of the hour here.
All right, very good. I appreciate everyone coming and asking questions and taking part in this. I think we'll add some more maybe next year. We've got our plan for this semester, but we might do some more on the sort of the Python tools just to give people
Sure.
sort of a primer on what we're talking about there. I know I've seen Zach Warner in our department do that in his graduate course and gives people but they were learning as they go along to do some basic programming. But the toolkit for video is powerful if you've got that, Greg, if you've got that basic Python knowledge, that then you add those tools and you got the video and you have the substantive questions. So you need those three pieces. But I think as Ed said, one other way is to do, there's many people out there who have the tools but not the questions. And when you pair up the political scientists who have the questions with the people who have the tools, you can, and that's what Ed and I have done over the years. It's a powerful combination. So, Andrea, I'll turn it back to you.
Fantastic. Okay, well, first of all, Dr. Delp, thank you so much for sharing your expertise in the area of video research. I know all of us have walked away from this probably going, okay, there's some really cool projects I can do with this. Do we have an email address that we can put up for you, Dr. Delp, that people can reach you at?
Oh, it's pretty simple. Just send it to ace@purdue.edu.
ace@purdue.edu. Fantastic.
Yeah.
Okay, well, I want to thank everyone for joining us today. Please join us for our next workshop, Video Analysis of Congressional Behavior with Dr. Bryce Dietrich, Assistant Professor at the University of Iowa. This workshop will dive into his video analysis of congressional behavior, and it is scheduled for February 28th at 2:30 p.m. And on March 25th at 3 p.m., we will feature Dr. Christopher Lucas from Washington University in St. Louis as he leads us through an introduction to audio analysis. So check your inbox for information on these workshops. You can also check us out on Twitter and Instagram. And
eventually we will post Ed's recording on our website here. So, and Andrea can give more information on that too.
Absolutely.
Good.
So to download the slides and software from today, I put the link up there. I'm going to leave that in the chat or in the on the screen while everybody starts to close down for the day. So, and thank you again for joining us. If you'd like to continue growing your knowledge of the video research methods and analysis, please keep an eye out for the information to come into your inbox, or you can reach out to us at Center for C-SPAN at purdue.edu. Again, you can check us out on Instagram and Twitter where we update our information regularly. Thank you all very much. Dr. Delp, thank you so much for your time today.